Okay, so I've started recording. People are coming in, so I just spend, as always, 2-3 minutes introducing the group, and then I'll hand over to our speakers for today. So yeah, welcome everyone back to the Multi-Agent Systems talk series, organized by the Multi-Agent Systems Special Interest Group at the Alan Turing Institute. My name is Stefano Albrecht, and I organize these meetings together with Michael Wooldridge from Oxford University. So just a couple of slides here to tell you, give you some background. So yeah, we are the special interest group in multi-agent systems research, organized at the Alan Turing Institute. The creation of this interest group followed a initial symposium or a mini conference that took place at the Turing Institute more than a year ago now, on the 24th of February. And it was a very good meeting. We had a lot of people coming together from across the UK, and the idea is that we want to be a national sort of a meeting point for university and industry laboratories who are interested in multi-agent systems research or applications. And you can find the URL to the website at the bottom of this slide here. So this is a summary of the activities, basically revolving around three things. We organize meetings and talk series. So far we've had this one symposium. We'd like to repeat this, but under the current circumstances, I think it's not clear when this will happen again, but hopefully soon. And in the meantime, we're doing these online talks, which are also uploaded to a new YouTube channel. We have created a virtual map where we've pinned down all the multi-agent systems focused research labs in the UK that we are aware of. If you are a lab that's not on this map yet and you'd like to be listed with some details, please get in touch with us and we can add you to this map as well. So you can go on this map and find out about the details and research interests. And there's quite a lot going on in the UK. And then we also have a mailing list that can be used by everyone to distribute opportunities, ideally UK focused opportunities for grants, jobs, and so on. And again, you find the URL to our website at the bottom here. So this is just a very brief introduction. And now I have a great pleasure to very briefly, as always, just introduce our two speakers. Today we have two speakers from two different institutions, both based in Edinburgh. First, I'm introducing Professor Helen Hastie, who is a professor of computer science at Heriot-Watt University, which is in Edinburgh, and also Professor Subramanian Ramamoorthy, aka Ram, who is a professor of robotics at the University of Edinburgh. And with that, I'm first going to hand over to Helen, who will introduce the UK Research and Innovation Programme in Trustworthy Autonomous Systems. And then the two of them will deliver two talks about the two new research nodes that are happening inside this program. So it's very exciting and has close links to multi-agent systems research. We'll be hearing about some challenges that these programs are aiming to tackle. Okay, with this, I'm handing over to Helen. And Helen, I think now you can start sharing your slides.
Thanks, Stephanie. Okay, so thank you for that warm welcome. So I'm going to talk about trustworthy autonomous systems from the human perspective. But before I do that, I'm just going to give you an overview of the UK-wide programme. So this is called Trustworthy Autonomous Systems, and there's one hub and 6 nodes. So Ram and I lead a node each. So I'm going to be talking about the trust node, which is all about the human aspect, and Ram is going to talk about the governance and regulation. So before that, I'm going to give a brief overview of the hub. I don't claim to be an expert on what is going on in the hub because it's a very big program, but there's a picture of Gopal, who's the PI. So if you have any questions about the hub program or how to get involved, you can go to that website or contact Gopal. So I'm just going to give you a brief overview. So the hub is led by Southampton, but also involves Nottingham and King's College London. And their ethos is around realizing industrial and social benefits of autonomous systems, saying they must be trustworthy by design. So judge both through objective processes, but also subjective lens. So I'm going to talk a little bit more about the subjective lens and in particular the users in my talk. So it's the £33 million UKRI funded project. As I mentioned, it's UK wide. It's one of the largest initiatives in the world, we think, for trustworthy autonomous systems. It's over 20 UK universities involved, over 100 industry partners across all the hubs and nodes. And each node, we've got about 3 million to run a 3.5 year program, and the hub has about 12 million. So the idea around the program, and UKRI was very, very keen on this, is that it's multidisciplinary. So in my node alone, we have cognitive science scientists, psychologists, engineers, computer scientists, linguists. You know, it's every single node is multidisciplinary. So across the whole program, we're talking about a lot of interdisciplinarity going on. So that's great. So there's the hub, and then there's 6 nodes on functionality, governance, regulation, resilience, security, trust, and verifiability. And I've listed there the PIs. If you're interested, you can contact them. There was supposed to be one on responsibility, but I don't believe that wasn't funded in the first round, but there was another call that closed actually last week. And so there's going to be smaller node-like projects that are going to come out of that. So that's still to be announced. Okay, so that's kind of the overall task program. UKRI defining 3 broad challenges that they want us to address. So improve rather than harm our physical and mental well-being, safeguard rather than undermine our personal freedom, and benefit rather than damage our society and economy. So those are the grander challenges. And across the hub and nodes, there's lots of different kind of research topics, research foci. So I'm just making sure I can, okay. So we've just listed them here. I know there's a lot going on in this slide, but if there's something you're particularly interested in, then everybody's open to you know, email and contact the nodes, so you can discuss this further. But so there's ones around design processes, operations, societal acceptances, etc. Okay. So the key sectors across the program are numerous. So I'm just going to highlight the ones that I'm going to talk about. So we're focusing on healthcare, industrial environments that are remote, hazardous, and also kind of social acceptable trusted devices and robots. And then RAM, and also creative industry, yeah. And then RAM in red, autonomous vehicles, healthcare, and also IoT to a certain extent. I'll leave him to talk about that in the second part of the talk. Okay, so how can you get involved if you're interested? There are a number of programs, really the ones outside the hub and node start at these pump priming calls. So there was one call earlier this year that's already been funded and announced, but Gopal has told me that there will be one later on in the year. So these are small projects, typically about 150K, that you can apply for even if you're outside the hub and node. And there is a large emphasis on multi-agents. So if you're interested and not sure whether your work or proposal aligns, then please, feel free to contact me. I don't mind having a discussion about that. And then they also want input into these grand challenges, and there'll be workshops apparently going on where you can get involved. And there is a skills program as well that other institutes can get involved with as well. But as I said, I'm not an expert on the hub, so you can go to that website or email the contact there if you want any more information about that. Okay, so I'm now going to move on to the node that I'm leading. So this is with Heriot Watt, Edinburgh, Imperial College London, and University of Manchester. And I said before, very multidisciplinary team. So we have Professor Angelo Canglosi, who's cognitive science, psychology background, as well as computer science and robotics. We have Yanis Demeris from Imperial College London, who's more of an engineering background. And then the third co-I is Professor Tusha Rajendran, who's from psychology at Heriot Watt. So that's our team, lots of talented PDRAs and PhD candidates. And we are expanding, we're still recruiting, so we only just started the project. So what I'm going to talk about today is quite a bit of ongoing work, because we have, we are still getting started, but hopefully there's some things of interest. Okay, so what is trust? I love this picture, it kind of summarizes the last few years. So there are lots of different definitions of trust, and what we're looking at are two definitions that we've kind of picked up because we think they align quite well with autonomy. So the first one is the willingness to accept one's vulnerability and rely on the behavior of another. And then the second one from Mayer is about, the irrespective of the ability to monitor or control the other party. So you can't always control the autonomous system. That's part of the essence of instilling autonomy in the system or the robot. But you still are vulnerable potentially to their actions. So these are the two kind of definitions of trust that we're looking at. And then human robot trust. So trust, again, is an attitude that the agent will perform as expected and can be relied upon to reach their goal. So trust can be quickly gained. We've seen that through something called automation bias, which has been known about for a number of years. So people typically initially trust automation. So if you get in your car, you touch your GPS to get you where you want to go. So whether that's the same for all autonomous systems, we're not quite sure yet. But what is clear that trust can be quickly lost. So trust breaks down when there's an error, or even if it's more subtle, if there's a mismatch between kind of representations or the mental model of what the system can do. So what we posit is that there's a need for this kind of shared mutual understanding of the task and the world. And bear in mind that this can be dynamic and can be uncontrolled. And we're not just looking at blindly trusting these robots, that wouldn't be good. So we want to look at trust, but the appropriate level of trust, so not over trusting something and not under trusting it. How we manage that trust, and we think we can do that through interaction. So if we're thinking about this kind of mutual understanding, one theory that we're looking at is the theory of mind. So this has been intrinsically linked to trust. So theory of mind is the ability to infer beliefs, desires, and intentions of the other person. Sometimes it's called a bit like mind reading, but it's not mind reading because we can't read minds. But what we can do is infer these aspects from people's behavior. And if we can get robots to do that, then I think we can move forward in defining this kind of trusting relationship between robots and humans. So where mistrust can happen is if there is a mix-up between how these two parties understand the situation. And how do humans resolve that? Well, they have a discussion and then they have an interaction and they come to a mutual understanding. So you can imagine this in some kind of task, collaborative task, like building IKEA furniture or something like that. Okay, so theory of mind. So there's a couple of orders of theory of mind. So the first order is I think, she thinks. Second order is I think the robot thinks that I think, and this can go on and on. But these are kind of the two orders that we're looking at instilling in our cognitive models. Okay, so the key research questions that we're looking at is we want to create a cognitive architecture that includes a variety of factors, including theory of mind. Can we define a set of principles of how trust is acquired over time, adapted to context, to errors, to the environment, to new users? And can we create these adaptive systems that can move forward through transparent interaction? And then how do we evaluate our system? Can we reliably measure trust in the other person? I mean, either non-intrusive ways or subjective and objective measures. So there's kind of these three areas that we're looking at. So our program of work is focused around these three areas. So we've got three work packages: the model, adapt, and validate. And we have a wide range of platforms that we're going to be looking at. And the applications are going to be cross-sector. So we've defined these applications in terms of proximity to the user. So for remote hazardous, we want the operator to be far from the actual robot. And then getting more closer together, working together, kind of cobots, tutors, companions, and then even more closely, we're looking at healthcare, assisted living, rehabilitation, and these types of things. So it's quite an ambitious project. So what I'm going to talk about now is each of these pillars and kind of the work that we're looking at addressing and what we've done so far. So the first one is cognitive models of trust. So we want to base this on foundations from psychology and cognitive science. So we were hoping to run some experiments with humans, but we're not allowed to do that because of lockdown. So we're working on some other aspects that I'll explain. And then we're going to build this cognitive architecture for trust. And then the third aspect is around transparent interaction. So transparent interaction that would feed into the cognitive model. Okay, so ongoing activities. Basically, we're doing some studies using Prolific, which is kind of crowdsourced platform. And one of them is around the theory of mind study. We've got the maze study. So some aspects that we're looking at is, would you trust a robot showing theory of mind versus one that doesn't explain kind of what it's thinking? When you're trying to get out of a maze, would you still trust it after it makes a mistake? And how do individuals' propensity to trust and attitudes to robots affect trust? So we're all individuals, and we all have different propensity to trust humans, and we think that maps over to robots as well. So that's really important moving forward. And then we're going to work on this cognitive architecture for trust, starting in the summer. And this is based on Angelo Cangelussi's prior work, where he's used Bayesian networks to model theory of mind. And then combining Bayesian approaches for theory models of theory of mind with simulation-based models of theory of mind. So to blending the top-down and the bottom-up mechanisms. So if you have any questions about theory of mind and cognitive architectures, then Angelo will, of course, open to talking to you. Okay, so moving on, other activities. So we are trying to define this questionnaire for propensity to trust using a Delphi method, and this is work with Edinburgh Uni, Swansea and King's College London. So this hasn't really been well defined. How do we measure accurately people's propensity to trust? So that's something that we're looking at, and hopefully that will be adopted in the variety of fields that are looking at trust. And then we're looking at explanations. So explanations are very important in terms of transparency. And we're seeing standards coming out, such as the IEEE P7001, transparency for autonomous systems, and explanations was a key part of that. So autonomous systems need to explain their decision-making process. And how do we do that? We can do that with natural language. So that's one thing that we're looking at. And then over the summer, we're going to start to explore different dialogue and interaction strategies that can help manage trust. So here's an example of a study that we did for a COVID triage robot. So this is a robot that would be, for example, at a hospital and either decide to go send you home because you're fine, or to hospitalize you, or send you on for further tests. And it was a video-based evaluation. So some findings, just to give you some examples, there was significantly higher trust in a robot that was more transparent. So transparency is a good thing for managing trust when the robot is behaving as it should do. When it's not behaving, if there's an error, then I think in our experiments, it was so obvious that there was an error, so that there wasn't really any difference in trust in that case. But we did find a difference in that people are more likely to make better decisions when there is a transparent interaction. So we're not just looking at subjective measures, asking the user, do you trust the robot now? We're also looking at objective measures, so behavioral indicators of trust, and decisions made after post-interaction are one of these indicators of trust. Okay, I'm just checking for time, how I'm doing. Right. So here's another study that we did pre-lockdown when we could have humans in the lab. So this is for an emergency response scenario. So this is where you're managing remote robots, and typically trust is lower when you're interacting with robots that are remote compared to those in close proximity. So it was quite a fun experiment. We looked at the fur hat robot. You can just about see it in the corner there, on the bottom right of that lower image, fur hat social robot versus a Google Home speaker. So some initial results, this paper's still under review, but initial results are general preference for robots in this scenario. And I think all these results have to be taken in the context of a specific scenario or task. So general preference for the robot, more trust was expressed towards the robot when they were asked to compare the robot with a smart speaker. and more broadly, kind of higher general task engagement and faster decisions with the robot. So that's another kind of example. And we're going to explore more the idea of these social cues, so shared attention, eye gaze, and how that affects trust in the user. Okay, so work package 3 is about adapting trust models. So we want to create personalized trust. We want to look at how this is maintained and transferred across new tasks and new people, and algorithms for repairing trust following failures. So work package 3 activities, we're looking at, this is Yanis Demiras's work, and he's looking at applications for doing the above what I've just talked about prior, for assistance. So he's worked on autonomous wheelchairs, and in particular he's looking at, handover autonomy, handover control, and hopefully the algorithms are transferable across domains. For the sake of time, I'm going to skip over the details of that. If you're interested in that, please, in these kind of aspects, please contact Yanis. Okay, and then the final work package that I'm going to talk about, because I want to give Ram some time, is the user validation and evaluation work package. So we've done some user requirements gathering, talking to our industry partners. What we want to do is to create an evaluation framework that can be universally accepted, and also provide experimental protocol for the rest of the program. And we're also looking at trust detection, automatic trust detection. So when we were in lockdown, we thought, well, what we could do is a meta-analysis, but then everybody started publishing meta-analyses. So we're focusing our meta-analysis on the HRI literature for trust, but looking at tasks and different contexts of the different experiments that have been happening. The evaluation framework, there are lots of subjective measures out there, lots of different questionnaires. So there's Gian, Schaefer, MDMT, and even HCT questionnaires going back a couple of decades. So it's all a bit of a mix. People aren't sure which one to use, which one is best. So we're doing a comparison and a review of subjective trust scales. We're looking at methods for natural language generation evaluations. If you're giving an explanation, how do we know it's good? How do we know it's good for the person? How do we know it's understandable and clear? Has the right content, the right lexicon? So we're looking at that. And that's a paper published at EACL recently. And then we're also looking at the idea of automatic trust detection. So this could be done to detect the human's level of trust online, so that we can adapt the interaction in real time. But we also could factor this into design recommendations for robots. So for example, there's different vocal variations in the literature that have been shown to influence trust, including naturalness of the robot voice, gender, accent, prosody, and context, and other factors. So we're looking at using machine learning methods to take these signals and to predict them using objective measures only. Okay, my final slide. So we did an initial requirements workshop where we'll discuss the various use cases that we're going to move forward on and the various factors. And I had a really good discussion about things like usability, the vulnerability, trust and decision making. These are all things that are important for our industry partners. So these are things that we really need to look at on the node. Okay, so that's me. Thank you very much. Hope I didn't go over too much. And I'll pass over to Ram.
Thank you, Helen. Yeah, so we'd like to have questions at the end of Ram's presentation, just to make sure we are within time. So if you do have questions now, please remember them, and you get a chance to ask later. But thanks again, Helen, and I think now we can hand over to Ram.
Can you see my slides?
Yes.
Okay. All right. Hello, everyone. Thank you for having me in this seminar series. So I should say, I think I was at the very first seminar that Stefano mentioned at the beginning, which was held physically at the Turing Institute, which was much nicer because I could see people and say hello to friends. So I virtually say hello to friends. And I should also start with the caveat that for those of you who have been in these previous talks that I've given on similar topics, you might see a little bit of overlap. Apologies for that, but I see a number of new faces in the audience, so hopefully it's interesting for everybody. So my role today is to talk to you about this new project that we've started. I say we've just started, but it's been 7 months officially. But as these things go under COVID times, it feels like we're just now getting started. So I'm the principal investigator for the UKRI node on trustworthy autonomous systems, governance and regulation. Now, when we first started this exercise, and as computer scientists, at least those of us who came from computer science type backgrounds, we talked about governance and regulation, we might have had quite different expectations of what would be covered under it. So I'm going to start today by telling you a little bit about what are the key questions as we see them, and what's really new about these questions. And then in the second half of my talk, I'll tell you a bit about the methodology that we are adopting. But firstly, I should say that our node is also collaborative, as Helen mentioned. I'm not going to individually list all of the partners because we actually have a number of COIs, but the universities involved are listed at the top of this slide. And we have a very diverse group of people, both in terms of geographic location and in terms of intellectual alignment. Okay. Now, what is the high-level goal for this particular node? Now, the entire program is defined around a theme that is not only timely, but also kind of deeply brings together many different issues. You know, what is trust, what is resilience, what is functionality, and so on. So defining exactly what each node is doing, it took us quite a bit of time. The way we are thinking about the remit of the governance and regulation node is to think about the processes by which one puts in place a framework for the development of AI systems. And a key part of that framework is informal and formal ways in which you govern the development of these systems. Now, I should start at this point by pointing out we're not just talking about, you know, what are the rules and regulations and how does the government make them. We are more asking the question, what is it that you would like to see of the system such that people will actually adopt them, both in terms of formal rules, as in you have to satisfy these things, but also informally that these are good practices. And in particular, how do we get at issues of responsibility and accountability, which is important for these systems to be adopted. And here we are referring to the idea that, and this is a theme I'll develop throughout my talk, most AI systems that those of us who are insiders to the AI community know well, most AI systems are fallible in the sense that they make mistakes. In new situations, they might not behave quite as expected. Then the governance question is, what do you want to do about this? How do you want to define what that behavior ought to be in these new situations, or what the failure modes should be? And then what do you want to put in place, not just in terms of the technical requirements, but also in terms of the organizational requirements, such that society as a whole can meaningfully utilize these systems? So we are thinking about it as frameworks for coming up with these ideas, and then building computational and software tools to help the ecosystem of developers and regulators actually do the design process in ways that are beneficial. So our project is structured in terms of 2 phases. In the first phase, we are solving these problems in terms of smaller chunks, smaller demonstrators, and building up the ideas. And our intention is that in a second phase, which would be the latter 18 months, we will bring all of these ideas together and situate them in the context of real world case studies where we directly work together with organizations that have a real stake in the regulatory process. This could be the equivalent of CAA, who's our project partner, and MHRA, whom we know through some of our advisors. So our project brings together a number of different disciplines. We have legal and social scholars. We have people who come from the machine learning and AI space who are specialists in causality, explainability, and tools like that, as well as from formal methods and NLP. While at the same time, even for ideas like accountability and responsibility, we have AI ethics specialists, people who have been looking at it from the social studies of AI and science. And we have a partner who's doing design ethnography to find out what do people actually do with these systems, not what the designer thinks they do. And I have listed a number of our external partners who will play a crucial role, especially in the phase 2 of our project. So whenever we talk about terms like autonomy and trust, it's worth pinning down what exactly do we mean, because it's like the proverbial elephant where everybody thinks of a different aspect of it. So to us, the point that's worth emphasizing is that autonomous systems are AI-based systems or in some form automated systems that are affecting something tangible in the real world. And what is perhaps unique in the way we are thinking about it is that we are not just interested in the inner loop of the system, but also the outer loop of how the system comes to be developed and how it comes to be used. And trustworthiness for us is a very multifaceted concept. I think it's perhaps a distraction to try to pin it down too narrowly. And all we will say is that it is very clear that achieving trustworthiness or trustedness is essentially through a process of design, both during the design of the system itself, but also the design of the processes and mechanisms by which, when the system doesn't work, then the diverse stakeholders have recourse to make the system do something that is better. And it is worth acknowledging, while we are on this point, that autonomous systems have a long history. We sometimes pretend in the media as though it's all entirely new, but actually it's not. And here are a few examples of automated systems going back centuries. And the point is that we have slowly come to the point when the systems have become more capable and much more widely adopted. So why do we have a new program now, and why are we asking these questions now? So a few things have happened through the process by which these systems have come to be deployed. So we've all started to see autonomous systems on the roads, in warehouses, as trading agents. And what has increasingly begun to happen is that the effect of these systems is being felt by a much broader range of stakeholders. So it used to be that the only people who cared about it and who were affected by it were a set of insiders in a small community. But today, I might have nothing to do with a self-driving car, but I might be worried about my safety if it misbehaves on the road, and likewise with trading agents and markets. And so to the extent that these are becoming wide social problems, we are asking the question, how do you want to define the workflows and the design flows in such a way that you can actually address this? On a more technical side, what has begun to happen more recently, even in comparison to maybe 20 years ago, the kind of AI systems we had, is that we are seeing crucial shifts, such as from models and specifications to data and labels. Even just the process by which one talks about specifying what a system ought to do has completely changed. And we are now seeing systems where nobody sits down and writes down requirements in quite the same way unless they are forced to. The second thing we are seeing is almost all of these systems, because of these possibilities, are continually deployed and kind of evolved on the fly, which completely questions processes by which previous regulatory frameworks have been put in place. So there are many new questions to be addressed. But it's also worth acknowledging that while there are new things, some things remain the same. We are talking about AI and new technologies, but an AI system is still a software-based system. And to the extent that there are well understood procedures for how to think about the development of a complicated system, that is probably still true of AI. The mechanics of individual components have changed quite a bit, but we still want to think about this entire outer loop. So when I use the term outer loop, my point was that we are not just talking about, as we do in some machine learning circles, whether we can build an adversarial free kind of robust machine learning algorithm. We are asking the full question of, knowing that this will inevitably have errors, what do we want of the full system, and how do we think about that as well? And we are not alone in this. Here are examples of number of worldwide efforts, across the board from different countries, different sectors, that are all asking similar questions about how the framework should be thought about. So what specifically will we focus on when it comes to the nitty-gritty within our node? We are interested in asking the question, to the extent that AI-based systems are systems of complex software, and they're taking the place of conventional devices. As an example, software is now a medical device, and medical device regulation doesn't immediately take into account what to do with software. So we want to cope with these kinds of issues. On a much more technical and nuanced front, we want to ask the question, how do these communities, developers, users, regulators, and so on, communicate and, much more importantly, negotiate levels of uncertainty, reliability, risk, and various forms of fallibility of these systems? And then to the extent that there are no real specifications in some of these systems, how do we want to cope with the specification gaps and hence the responsibility gaps? So to ground this all a little bit, I'm going to use an example that if you've come to some of my previous talks, maybe you've seen bits of this before, but it's worth repeating. So I've had quite a heavy involvement in the area of autonomous vehicles over the past 5 years as part of a startup company called 5AI. Most of you at least would have informal familiarity with what an autonomous car is. It's just a car like every other car you've been in, except that the driving, decision making, and the control aspects are taken over by an AI system. And what is crucial about this is that although it's just an engineering system and one could envision it in terms of block diagrams like this, the details of this you need not worry about, except to note that the operation of a system like this is not just about the code that's inside the car, but much, much more crucially about the world models of what is happening outside the car, how the car has to interact with other people, and what that implies for the actual achievable behavior of these kinds of systems. So on the one hand, if you just think about what it means to develop a system such as this, you will realize that there are a number of machine learning modules that are being used crucially in perception that are fallible for reasons of the difficulty of achieving common sense in these systems. But also in the way that these systems actually interact with an environment. There are lots of other agents who are not under our control. There are lots of environmental factors that are extremely difficult to cope with, which all go to mean that it takes enormous amount of effort just to keep the error rates to the point that one can think about this system in some way that the behavior can actually be described. And so the crucial question to ask is, all of these systems are highly interactive, complex systems in a complex environment. What are the effects of possible errors on perception, prediction, understanding, and so on the closed loop behavior in the open environment? And when we get these wrong, it can have catastrophic effects. So the point of governance and regulation is to ask, how would the developer cope with this? How would a regulator say what is required of the developer? And how would an end user say what is required? So to us, the regulatory and governance questions arise from a question that is first and foremost for the developers, which is there's a huge difference between what current AI-based systems achieve in terms of error rates and fallibility and what people seem to achieve. This is true irrespective of the specific technology we are talking about. And if you were inside one of these development teams, then you would think in terms of the fact that there's a technical challenge to jump this. But if you are sitting with the regulator's hat on, you're trying to ask the question, how do I kind of manage this process? And also, how do I want to put in boundaries such that the community can safely try to jump through this hoop without damaging all of the stakeholders along the way? Now, one knee-jerk response that one could take, and this is one regulatory option, is to simply say we're not going to allow any autonomy at all, or that you take an intermediate stance, such as which would be a simplistic view of regulation, which is the humans in control, and that's that. They take responsibility. But it's been shown in a number of domains, in aviation, finance, and so on, that this is a terrible approach. For a variety of reasons, including the fact that skill deteriorates if people aren't actively working and so on. So the main point of the slide is to say that there are no simple answers to how you want to cope with these issues in AI. One actually has to think deeply about the system and where the errors come from, what the causal factors are, and how people come to accept them. That then is the real technical challenge for our node. So the way we are approaching this is by saying that we're going to take a case studies based approach. We're going to pick a few big application domains, which I'll tell you about in the later part of this talk. And we're going to use as a mechanism, full system simulations and reference implementations of AI-based systems. which are going to be informed by qualitative studies of actually sitting down with stakeholders in these domains and telling us what the requirements might be, not just in the technical sense, but also the organizational sense. And then the fact that we have these artifacts would allow us to envision the possibilities and engage with the stakeholders better than just asking open-ended questions. And so the input to the buildup of these kind of case study systems would be, ethnography, existing legal frameworks, scenario descriptions in a technical sense, incident reports from previous such systems. And what will come out is an understanding of what would responsible development of these kinds of systems look like. Evidence-based, for instance, what are good ways of achieving high reliability? What did it take? What kind of specifications did you have to use? And then governance and policy recommendations for how exactly the guidelines for usage and design of these systems should be put in place. So let me now give you a couple of vignettes of sort of work we are drawing on so that I can tell you precisely in concrete terms what case studies we might look at. So the first vignette is this idea, and this refers to this process of how exactly an end user who's not exactly a computer science specialist can work with this process of putting together these full system simulations in a domain. So acknowledging that specifications don't exist up front, you have to interactively elicit them from people and give people mechanisms to tell us what the tasks are. So we've done some work recently on finding ways in which once a robot is being taught how to do a task, in this case, the robot has learned how to do the task from demonstration, we can incrementally elaborate what that task is by giving additional task specifications as the robot goes along. And in this particular work, the technical device was to find an intermediate temporal logic form, which is then used to guide the learning process. So at one level, the system is a machine learning system, which those of you who are familiar with robotics would recognize a loop like this, which involves vision-based control of a robot and a parameterization in terms of motion synthesis. But the crucial addition here is that we have both the low-level machine learning training loss, but also a mechanism by which the logical additional specifications have been turned into a loss function, which can be put into the training process through an adversarial training process. This allows us to, find ways in which we can combine both the symbolic specifications that's incrementally arriving and the standard machine learning process, improving the robustness. And this is just a vignette to give you an idea of how we might think about these kinds of problems. The problem we are actually interested in one of our major case studies is to think about the autonomy of an unmanned aerial vehicle. And we are working with a number of different stakeholders in this area. We are using tools that come from the aviation sector, from DRISC and NASA, and the procedures for putting safety cases in place. We are using state-of-the-art simulation systems such as AirSim and Simulink. And the expectation is that by the time we end this project, on this strand of the project, we would be inside a regulatory sandbox with somebody like the CAA and showing how is it that you can find a safety case in an evidence base, not just for how the system normally operates, but how it gracefully fails and what it must do. And then in that process, negotiate the safety requirements and things that might have been left out in the initial design processes. And that is a crucial interaction, which is perhaps worth thinking about for a community of multi-agent systems researchers. Another vignette, which will allow me to introduce my second case study, is thinking about questions of explainability and causal factors. So everybody in AI by now is familiar with problems of why we need systems to be explainable. There are a number of different methods out there. Oftentimes, the focus is on saying, there are these black box training methods that are working very well, and I want to somehow expose what the model has learned. But that's a little bit insufficient if you think about it from the point of view of the full ecosystem. That's not the question people are really asking. What people are really asking is, I know that there are error rates involved. For instance, in medicine, I know that there is a possibility that I might not detect cancer when I'm doing biopsy slide analysis. I want to understand how we should negotiate and understand these error rates. And then I want explanations with respect to that. So one activity within our node would be to think about the different ways in which explainability can be looked at. It can be looked at in terms of conditional probabilities. It can be looked at in terms of counterfactuals. We can ask questions in terms of what happens if I delete data points. Now, in AI, each of these is a well understood sub-community, and there are lots of papers out there. So the question for us is, how do we put this together inside a development process such that we can answer questions that go at the next level up? And so, for instance, when we're engaging with NHS, the kind of question we want to ask is, how is the error budget actually, allocated between the human expert, the automated machine, different organizational units, and then how can the organization as a whole take responsibility, for instance, of the screening process being good? So that actually forms one of our big case study domains. So we're engaging actively with a couple of NHS teams and companies such as Optos, who are major suppliers to the NHS screening process. So we're looking at, in one instance, we're speaking to a team that are in charge of diabetic retinopathy screening in Scotland. In another instance, we are speaking to the team that are in charge of HPV cancer screening. And in both of these situations, we are trying to understand how these teams can come to communicate and negotiate uncertainties and understand their propagation through the causal chains. If you do slide microscopy and then an expert gets involved and then they have a team. So how exactly do we think about uncertainty propagation? And then what are the kind of social aspects of this? So how do people take responsibility? Where does liability rest? If you have multiple organizations, how does the law get involved? And we are also interested in questions such as, bias, which might come in from if you have extremely unbalanced data, and if certain communities were being, disproportionately affected by errors in these systems, how does one actually negotiate that in the governance process? So that's an important question for us. So to conclude, this is a fairly broad scoped project, and we are interested in creating a framework and tools for identifying different responsibilities and elucidating causal chains. And so causal chains of understanding the fallibility of these AI systems. The outcome would be that we'll both have proposals for informal and formal governance, which would be the legal and social side, and an evidence-based and computational tools for how exactly to cope with this in the development process, such that we can, as an ecosystem, achieve better governance. So I will stop with that, and thank you for your attention. I'm very happy to take questions if you have any.